Hello, today we'll be going over Educational CodeForces Round 104, Problem D, Pythagorean Triples. Now, in this problem statement, you're essentially given a number of test cases, and for each test case, you're given one integer n. Now, for each n, you want to find the amount of triples, such that each number in the triple is less than or equal to n, and the numbers in the triple satisfy c equals a squared minus b, and c equals a squared plus b squared. Now, I'll be going a lot more in depth about these conditions in my solution, so this is just a brief overview, but I highly recommend you watch through my solution, as my solution is 4 lines of code, and it is a completely mathematical solution with proofs. So, with all that being stated, let's dive right into it. Now let's go over the solution to this problem. So we want to find a Pythagorean triple that satisfies Vanya's equation, which is, if we label this as equation 1, c is equal to a squared minus b, and satisfies the Pythagorean theorem, which is c squared equals a squared plus b squared. So to find this triple, let's solve both equations. Let's look at Vanya's equation first. So we know that the Pythagorean theorem has a c squared. So what can we do to Vanya's equation to maybe get a c squared? Let's square both sides of it. So we know that c squared is equal to a squared minus b whole square. So now let's solve the right-hand side of this. A squared minus b whole squared is a to the 4th minus 2a squared b plus b squared. And that is equal to c squared. So now, the reason why we will do this is because we notice that there's a c squared here, and there's a c squared in the original Pythagorean theorem. So now, we can set this part of the first equation equivalent to this part of the Pythagorean theorem, because they're both equal to c squared. So now, taking both of those and setting them equivalent to each other, we get a to the 4th minus 2a squared b plus b squared equals a squared plus b squared. We can subtract a b squared from both sides and just cancel that out. So now we're left with this equation. A to the 4th minus 2a squared b is equal to a squared. We can divide both sides by a squared because they both have that same common factor. So we'll get a squared minus 2b is equal to 1 once we divide both sides of this equation by a squared. Now we have a simple equation here which we can solve for. A squared is equal to 2b plus 1 by adding 2b to both sides and taking the square root, we get a is equal to square root of 2b plus 1. So now we have solved for a. Let's solve for c now. So we know that c is equal to a squared minus b, and this comes from equation 1, Vanya's equation. So now if we just substitute a in there, we'll get c is equal to a squared, which is square root of 2b plus 1 squared minus b, which leads c equal to 2b plus 1 minus b, or c is equal to b plus 1. So now if we write our Pythagorean triple in terms of a, b, c, we know that a is equal to square root of 2b plus 1. So we have square root of 2b plus 1. We know that b is just b. We leave it unchanged. And we know that c is equal to b plus 1. So this is the triple which we are trying to find. And we're trying to find all triples of this under the number n. So now the most confusing part about this is finding the amount of triples such that each number in this triple is an integer less than or equal to n. So let's take an example. Let n equal 6. Let's try and find how many solutions we can have. So we need each of these numbers to be less than or equal to 6. So we know that square root of 2b plus 1 is less than or equal to 6. b is less than or equal to 6, and b plus 1 is less than or equal to 6. Now, let's not focus on the first equation. Let's focus on these two inequalities. So from here, we notice that this one will give us b is less than or equal to 5. And out of these two, we can just take b is less than or equal to 5. Because we need a b that will satisfy both of these. And if b satisfies b is less than or equal to 5, Well, any number less than or equal to 5 is already less than or equal to 6. So we can just take this equation. B is less than or equal to 5. So now let's try and plug in some values b less than or equal to 5 and get some values of a. So we know that since b is a positive integer, b can be 1, 2, 3, 4, or 5. Let's plug that in. So b equal to 1, this will lead a equal to square root of 2 times 1 plus 1, which is root 3. b equal to 2, this will lead a equal to square root of 2 times 2 plus 1, which is equal to root 5. And if we keep on doing this, we will get a is equal to root 7. b equal to 4 leads a equal to root 9. b equal 5 leads a equal to root 11. So now we notice out of this that if we set b equal to 4, a is equal to square root 9. And square root 9 is just equal to 3. So that means a will be equal to 3. And this is the only Pythagorean triple that satisfies this, because the rest of these, like square root 7, square root 5, square root 3, these aren't integers, and we want integer solutions. The only integer solution we can get is if we let b equal to 4. If we let b equal to 4, then we get a is equal to 3, b equal to 4, and c is equal to b plus 1, right, as we already found up here. So then c will just be equal to 4 plus 1, which is 5. And this gives us our one triple. So now let's move on to finding solutions for the general case. For any integer n, how many triples do we have? Square root of 2b plus 1, b, and b plus 1, such that all numbers are less than or equal to n, and all of them are integers, positive integers. So from the previous example we had back here, we noticed that the maximum value of b can be n minus 1. And we get that by setting the third equation, b plus 1 less than or equal to n, b less than or equal to n minus 1. So now, what values of square root 2b plus 1 work? We notice that if b is a positive integer, then b plus 1 is a positive integer. Now, what we need to focus on is square root of 2b plus 1. Let's look at this more closely. Suppose that we have some value of b, such that when we plug it into a equal to square root of 2b plus 1, this is odd. So let's set square root of 2b plus 1 equal to an odd number. What happens when we square both of these? 2b plus 1 is equal to an odd number squared. Now, what do we know about an odd number squared? We know that an odd number times an odd number results in an odd number. For example, 3 times 3 results in 9, which is all three of these are odd. So we know that this odd number squared is going to be odd. What happens when we subtract 1? We know that an odd number minus an odd number is even, right? For example, when we take that same 9, we subtract 1, we get 8. 8 is even. So from here, we notice that this number, this whole number, is even. So therefore, when we get 2b is equal to odd number squared minus 1, this will be divisible by 2. So this will yield an integer value for b. So b will be some integer value. So from here, we can conclude that if a is an odd number, there will be a solution b that exists to this. For example, set a equal to 3. 3 is equal to square root 9, and set that equal to 2b plus 1. From here, we notice that if we set b equal to 4, these equations match. Let's look at a equal to 5. That's equal to square root of 25. Set this equal to square root of 2b plus 1. We notice that if we let b equal 12, this will match. For every single odd number, there will be a value of b that can satisfy this, such that a will also be an integer. Now, let's look at the values such that we have a as an even number. Let's let a equal square root of 2b plus 1, which is, let's say it's even, right? Let's say a is even. Then we know square root of 2b plus 1 is some even number. Square it. 2b plus 1 is equal to even number squared. We notice that the even number squared will be even because even times even is even, right? For example, 2 times 2 is equal to 4. All of these are even. So we know that this number here is some even number. Suppose we subtract 1. 2b is equal to even number squared minus 1. What happens when we subtract 1 from an even number? Even minus odd is odd. For example, suppose we take that 4 and we subtract 1 from it. This will turn it to the number 3. 3 is odd. Therefore, this value is odd. Now, what happens when you take an odd number and divide it by 2? We will not be able to get an integer. Therefore, there is no integer value of b that works such that we get an even value of a. So a cannot be even. So now let's move on to the easier part of the solution, where we're trying to find the amount of triples given all the information we know. We know that first a is odd. One thing we must clarify is that a cannot be equal to 1, because if we set 1 equal to 2b plus 1, we'll get that b is equal to 0, and b has to be a positive integer. So a is all odd numbers except for 1. So now this solution becomes clear, and we can write this in a couple of lines of code. First, let's find the largest possible value of a. So we know that the largest possible value of b is n minus 1, right? Because we know that b is less than or equal to n minus 1 from one of our previous observations. So let's just set b equal to n minus 1. That way we can find the largest value of a, which is equal to square root of 2b plus 1. Okay, so suppose that we have found the largest value of a. So remember, in n equal to 6, for example, we got that a is equal to square root of 2b plus 1, square root of 2 times 5 plus 1, root 11. Now, root 11 terminates to 3 point some number. We don't really care about that, what that is. But in C++ or any language, really, if you take the square root, it will just truncate it to an integer 3. Okay, now that we have found that integer, right? Suppose that this gets truncated and we find some integer. The solution becomes clear. All values of a less than or equal to that integer, which are odd, will be solutions. But we cannot include the number 1. So basically what we're saying is that solutions of a equal to 1, 2, and 3 exist. That is what we're saying right now. Now, let us look at our conditions. A is odd and a is unequal to 1. How many of these numbers are odd and how many of them are unequal to 1, right? So 1 is equal to 1, we cannot use that. 2 is even, we cannot use that, but 3 works. 3 is odd and is unequal to 1, so therefore they're one solution. So suppose we come back to this number 3. How many solutions can we get just by calculating it? We know that if we cannot include the number 1, there are 2 numbers which we can include, which is just 2 and 3. Now out of that, half of the numbers will be even and half of them will be odd. So we will divide that number by 2 to get one solution. Now this part might have been a little bit confusing, but suppose that we get b is equal to n minus 1, right? This is the largest value of b. When we substitute that into a, you will get square root of 2 times n minus 1 plus 1. Now this is the largest value of a, right? This is the largest value of a. So that means that suppose that this equals some number x, right? When we get it, it'll be like x dot 1, 2, 3, 4, x, and then some random decimal places after that. Let's ignore that, right? Let's just truncate it. We get x, because we want integer values. So now x. A can be any number, right? 1, 2, 3, dot, 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 all the way up to x, because that's the largest value. So now from here, we have the condition, a is odd, and a is unequal to 1. You know, a has to be odd, and a cannot be equal to 1. So let's just cross off 1 out of the bat. Now we know that each number is either even or odd, and that alternates. For example, 2 is even, 3 is odd. 4 will be even, 5 will be odd. So we know that x over 2 of the numbers in this original list are odd. We subtract 1 because we cannot include the number 1, and then this becomes our answer. I'm not actually going to type the code out one line by one line because we've already found out the majority of our code in our solution, so I'm just going to explain it. First, let's take in the amount of test cases, and for each test case, let's take in the value of n, right? And this is how, now the question becomes, how many triples can we find such that the three integers and the triple are less than or equal to n? First, remember we said b equal to n minus 1. Let's find the maximum value of b. Now let's find the maximum value of a. The maximum value of a is the square root of 2b plus 1, where b is maximal, therefore, since a depends on b, a will be maximal. Now from here, all the numbers from 1 to this square root of 2b plus 1 will work for a. But the thing is, we have to subtract 1, because we cannot include the number a equal to 1, because that will result in b being equal to 0. After we subtract that out, we divide by 2, because we notice we can use a parity argument. Each number in the list will either be even or odd, and this alternates. So half of the numbers will be even, half of them will be odd. And since we want a to be odd, we just divide that by 2, and then we print out our answer. And we can see that on the first attempt, this solution is accepted.